our first presenter, Anand Joshi. He's an industry veteran who is currently consulting with Tractica and other entities. His experience spans startups and business units in companies such as Alton Callsoft, Synopsys, LSI Logic, and Poseidon Design Systems. He has an MBA from UC Irvine after his EE degree from Virginia Tech. He's actively involved in computer vision and deep learning, and he's going to share his expertise on the AI chipset market with us. So welcome, Anand.
When Ira and Betty approached me, I thought this could be a good opportunity to talk to you and just explain what's going on in the world of AI and what can be done when it comes to packaging and semiconductor processing. Just a quick background about me. I've been fortunate enough to get into AI back in 2014 when nobody was talking about it. It started with a report on computer vision when I was trying to do a startup at a VC firm as an EIR, and before I knew, my phone started ringing. Intel, Nvidia, ARM, they were all my clients, and it hasn't actually stopped ringing since. So I've been fortunate enough to do 2-3 jobs at the same time. I've been working at Tractica as a analyst focusing on AI computer vision. I've also been working at many of the chip companies focusing on the product management, marketing. So I'm actually coming off of a stint at Wave Computing as we speak, and been working very closely with investors and startups as well, due diligence and startups and business plan and marketing, all of that. So quite deep into the whole AI and computer vision ecosystem as it pertains to chip. I come from chipset background myself. I'm a chip designer, so I understand the technology very well. So let me start by showing, mother of all the chipsets that's out there, if you will. This is a chip that's from a company called Cerebras. They are one of the well-known startups in AI. And what they have done is they have taken an entire wafer and converted that into a single chip. So the largest GPU, as you can see on the corner bottom there, is about 815 millimeters square today. This will be 46,225 millimeters square. And this is going to create all kinds of very, very interesting problems. I got some slides in the end. I'll explain you how this can be taken further and if this could be successful or not. But this is the direction the AI is taking the semiconductor world. And there is a reason for excitement is because the kind of problem that are being posed by AI are just simply not thought of before. And really the fundamental shift has to happen in thinking how we design chips and how we take it to the market. So let me tell you what AI acceleration is all about. It's essentially neural networks is the acceleration of neural networks is the word. So neural network at its very, very primitive stage is a perceptron, which is nothing more than AX plus B. If you remember your linear algebra, it's a simple AX plus B equation. And then what you do is you basically take that and you create layers and layers and layers on that. And eventually you have a feed forward network, a artificial neural network, a convolutional neural network. You have feedback networks, so your data is going almost like a sequential circuit. It goes out and comes back in. And it just gets complex and complex. Here, the yellow dot is really the input, and red is output. So even though it shows 2 dots here, in real life, that input could be your 1080p picture or 4K picture. So you got 2 million inputs right there. And then each one of the compute units can have multiples and millions of computation being done. So as you can see, it just keeps on multiplying with the architecture, and you go forward, you compute the results, you go backward, you go forward again, and there is a lot of computation that happens. And what that's leading to is that essentially every 3.5 months, the complexity is doubling. So this picture is from a company called OpenAI. They're a non-profit organization founded by some of the AI stalwarts in the industry. And what they did was that they plotted the state-of-the-art neural networks going back to 2012 to today. And this is the time that you would need for a training. So there is a phase called as training in networks and inference in networks. I'll talk about it in a minute. But AlexNet was really the first network where everything started. The computer vision accuracy suddenly became so good that everybody got suddenly interested in this, and it just went up from there. So today we are at AlphaGo, which is really a checkerboard game and there is like ridiculously high amount of computation you can do at every step. So there is a neural network that does that. But the bottom line is that every 3.5 months, the need for compute is increasing, and the numbers are ridiculously large. And in comparison, the Moore's law is ending. Used to be that when you go from node to node, every 12 to 18 months, you would get double the performance, half the size and all the good stuff. But as we are going toward these smaller nodes, first of all, the time it takes from going through 5 nanometer to 3 nanometer is not going to 18 months. It's more like 24 or 36 months. And it's only going to increase as you keep going. And then the increase, the reduction in node does not necessarily mean that your performance is going to double, because power is now, suddenly leakage power is in the place, so your power is not going to go as you would expect. So there is a huge gap in terms of what AI needs and what chip technology has to offer. And that's where all the problems begin. And the chipsets today, they all come in different shapes and sizes. So here the circumference of the circle really represents the market size, if you will. So in AI world, there are two parts. There is the training part and there is the inference part. So training is something that data scientists do. They basically teach the network to recognize an object or chart a course or solve any kind of problem. And then that network is taken by people on the field, and they use that to recognize objects or drive a car or whatever it may be. So depending on how you slice it, fundamentally there are 4 different kinds of problems. There is an enterprise training, enterprise inference, and then there is edge training and edge inference. So edge here refers to anything that sits on the edge, meaning a smartphone or a temperature sensor, tablet, TV, anything that's more fine-grained is an edge, whereas enterprise is anything that goes in the data center. So today we have CPU, GPU, FPGAs, and ASIC. And ASIC actually is sort of a misnomer here. It's in a traditional sense, I worked at LSI Logic, and to us ASIC had a very fixed functionality with very limited programmability. Here is ASIC is referring to the application specific, which is AI, but it is programmable. So it's a slightly confusing term, but nevertheless, it's designed to solve the AI acceleration problem. So that's where all the startup activity is. So they come in different shape and sizes. Each one has strengths. So for example, GPU is the only solution that you can use for training. There is nothing on the edge today that you can use for training. It's actually a very interesting problem to solve. I'm pretty sure there are some startups going after that. CPUs are, x86 has been there, ARM has been there, and they are doing well. FPGA, both Xilinx and Altera are doing well. And ASICs is where most of the startups are, Intel, Nirvana being the most prominent, which got acquired. So the needs of chipsets on the enterprise are very different from the needs on the edge. So what you need on the enterprise side is you need a very high compute capacity. Your power can go a little bit high, whereas on the edge you need low power. It has to be able to sustain a small battery and still support all the algorithms. And it gets even murkier. So CPUs, you can have a low power or enterprise, and then there is a sub-variant there which is DSP optimized, and that's what some of these players have started doing. Intel, for example, has a new chip out there. That's got a very large SIMD engine, which helps them accelerate some of the algorithms. ARM has a project Trillium, in which they're essentially giving you coprocessor along with their IP. So there are different approaches being taken at every architecture level. GPUs, for example, there are low power GPUs, Jetson Nano being sub 5 watt, enterprise GPU V100. FPGAs, there are 2 separate product lines for edge. And ASICs actually are slightly different kid on this block, if you will. The ASICs have been optimized for architectures or Marget or neural network or use case, whatever it may be. So there are like 100+ companies. But really what it means is that it's posing a lot of very interesting and new challenges for semiconductor processing. And so let's take a case of this Pascal and Volta GPU. So this is the flagship product from NVIDIA. And it's actually selling for around $10,000. It's the most advanced product today, the Volta GPU. Pascal is actually slightly outdated, but I kept there for comparison. So that one, the Pascal was done in 16 and 14 nanometer. Volta is done in 12 nanometer. And the size, has gone from 471 to 815 millimeter square. The performance has increased from 10 teraflops to 120 tensor flops. It's a very different technical term. I will not get into that, but in essence, there is a 12-fold increase in the performance. But notice the power has stayed the same. And there is a reason for that. The reason being the PCI Express slot on any of your server can only give you 250 watt maximum, even with additional power socket. And so that's really the limitation. They had to stop at 120 teraflop because there was nothing available to support the power. And so that immediately leads to all kinds of problems, right? So if there is a new, latest GPU that's coming out today, can they keep going on that curve? Can they go to 1,000 or 1,200 millimeter square? If so, what is the power? They have to stay within 250 because PCIe 3 to 4 has been slow, and 4 to 5 is even slower. And so now they are stuck with the power limitation, and they have to design their chip. At the same time, they have to keep increasing the performance. And is the node, going to next lower node going to help them? 7 nanometer or whatever, your leakage power is there. So again, it's not going to help you in terms of power. Pricing. Thankfully, this particular market has no pricing, pressure. People are willing to pay $10,000. But it is not sustainable. There is a lot of startups coming out there. There is a revolt. If you talk to some customers, they'll come and say, we don't like NVIDIA because of their pricing strategies. And so this is all not sustainable. All of this has to be invented. There is also the power and heat, which again is a very, very interesting problem. So what I have in the picture here is a DGX2. So DGX2 is a workstation from NVIDIA, which is state-of-the-art for AI chipset training, AI algorithm training. Each GPU has a 250 watt of power. So this particular server has 16 GPUs. They're all connected by PCIe fabric. In this case, that's NVLink. They have DRAMs, and then there is a x86 CPU that's basically controlling all of this, right? So the system power, the box, actually is a 10U box, and it consumes 10 kilowatts. And I've been fortunate enough to go into a data center where they had racks and racks of these DGX2, and that one was actually running at 10 megawatt. And you wouldn't believe that the noise inside of that data center was comparable to a jet. It was not even funny. We had to put on noise blockers. But the point being, this is today. Tomorrow, where do we go from here? Already we are stretching the limit. 10 megawatt data center is not everybody's play. And tomorrow we're going to 100 megawatt, and that's just not sustainable. Then there is this whole question about cooling, right? Air versus liquid. And then what infrastructure do you need? How do you cool it? What happens to the price, right? How do you cool at the chip level? How do you cool at the system level? There is all kinds of problems that are going to come, and we'll just have to watch and see what innovations take place. There is another problem with the chipsets on the edge. So what these guys are doing, so these are all startups. They're going after alternate ways of solving the AI acceleration problem. So what Sentient is doing is that they are taking analog multiplier and trying to replace the digital MAC. Light Matter is trying to do the same thing using optics. Now, where is the technology to manufacture that? Yeah, you can do 1 or 2 in the lab, but how do you mass produce them? What is the price point? What is the foundry need? How do you set up infrastructure? RAIN actually is doing even more advanced things. They have a what is called as neuromorphics. So neuromorphics is a very fundamentally different way of solving the neural networks. What you try to do is combine the memory and compute together, and then you try to mimic your brain's behavior, sort of connect each neuron to another neuron with a synapse, and there is activities and spikes and all of that. And memristors, they're obviously very early phases. They were funded by DARPA. And they're claiming that it's a nanotechnology. Again, how do you go into production with nanotechnology? What kind of fags do you need? So there is all kinds of issues happening, and on the edge, because battery operated can only take certain milliwatts, if you have a battery operated devices that you want to run for 6 months or 1 year, you cannot really take more than a few milliwatts. And if you're in operation continuously, you are just limited by the power that's available. So you have to, there is only so much width or depth you can go with the technology shrinkage, but beyond that, you have to innovate this, and we are getting there very, very fast. And again, there is these fundamental problems remain, that even if you have a fab, what is the yield, right? What are the other means of creating your fab? The edge versus enterprise, the problem, right? So how do these stack up? So edge chipsets by definition are small. How do you make actually a big chipset out of this that you can sell to enterprise boxes? So all kinds of problems, very interesting problems to be faced, right? And so I thought I'll leave you with this. I showed to you this in the beginning, and I was actually very impressed when Andrew, actually it was his chief scientist, who showed this at Hot Chips. This is almost out-of-box thinking, when it comes to solving the AI acceleration problem. Everybody actually suffers quite a bit when you go from computation within a chip to a different chip, because you have to go through, either chip-to-chip interconnect or the system interconnect PCI Express, and suddenly everything that you gain within the chip is lost. So instead, they just took the die and carved out, this is actually 84 chips, the largest size of square they can get. And this whole thing is a chip. And it's actually a fantastic thinking, because now if they are able to do this, they will be way ahead of everybody else with some very, very innovative product. But to me, this is like opening Pandora's box, right? There is a reason why chip industry stayed at 600, 700, 800 millimeter square, because they could not solve the problem. And so there are a lot of problems pertaining to yield, the connectivity within die to die, how do you assemble a package, how do you power this, right? This is like 57 times bigger than today's largest chip, which is NVIDIA's V100 GPU. And so, these are some of the solutions that they have proposed. I thought they were very, very interesting. So first of all, when you do a wafer, you keep space between die to die, so you can cut it and do your connectivity, all of that, right? What they did was that they actually laid out connectors in between. And so using those connectors, you can actually connect chip to chip. And so you can make it a single die to die, and it becomes a single compute unit. So that was one very interesting innovation. But then there is issues with yield, right? So what if this chip percent that doesn't work? Or what if the part within the chip fails, right? So what they have done is that they have created 400,000 processing elements, essentially ALUs, within these 84 chips. So even though it looks like a chip, it's likely a smaller chip inside of that with a connectivity. And the same connectivity repeats on the die level. And so via software, they can actually program the network on chip, so that if there is a issue on this die, they just go around it. And so very, very interesting way of solving the problem. So that picture on the left actually says that. So if you have a defect in the middle, they just route it to the next chip and goes there. So again, what they're saying is that TSMC yield is almost close to 100%. Given that this is 16 nanometer, I would tend to believe that if not 100, it's fairly high. But as you go to next lower nodes, it's going to get more and more difficult. And then there is the whole problem with packaging. There is nothing in the world that exists that will package your entire die. So there was nothing that would place it correctly or position it correctly or give them connectors, all of that. So they had to invent the whole packaging methodology and invent new tools with TSMC. And then there is the whole question about how do you route the power. So this wafer, if it works, is going to be like 10 or 15 kilowatt, and that's like 50 amps of power. There is no way you can get that there. So what they have done is that they have taken this die, they came up with this connector material, whatever their invention is, so that it expands at the same rate as the die, as the wafer. And then they place that assembly on a PCB board. They drill holes from the PCB, so the power is actually going from top to bottom, so they don't have to route the power on the wafer itself. And then they put cold plate at the top to control the heat. And to me, that heat really, is really going to be a serious problem, because what they're proposing is essentially a heat exchange mechanism. So there will be a water that will be forced through the chip. It will go into the cold plate there, and then it will go to heat exchange, and it will keep circulating. So it will maintain a constant temperature at some point. To me, it's a very ingenious solution. In reality, I really don't know if that is going to work or not. But nevertheless, it's a very different way of solving the heat problem that we're going to face pretty soon. And and there is another problem there, that today's chips are designed to operate at certain voltage levels. Let's say so at a certain temperature. So 0 to 70 or 25 to 50, 55, whatever that may be. The cold plate method they are doing, it's very likely that they will be going beyond the normal operating temperature, just because there is so much happening within the chip and so much power that's being consumed. And so there is another problem. What is the mean time between failure if they're constantly operating at 100 degrees Celsius, for example, right? I mean, it might run for a short period of time, but then it'll fail. So again, we are just opening all kinds of new problems when it comes to the chipset manufacturing and semiconductors and all of that. And it's just the beginning. I mean, to me, this AI is really in its early stages, and it's going to get worse. And that's pretty much all I had. So.